What if the end of a black hole isn't destruction, but survival? For more than 50 years, physicists have faced a strange problem. Black holes may eventually disappear, but if they do, they seem to destroy information that quantum mechanics says should never truly disappear. Now, a 2026 theoretical study suggests a very different ending. The black hole may simply stop evaporating, and what remains could be incredibly tiny, while still holding an enormous amount of information. To understand why this matters, we first need one strange rule of quantum physics. Information cannot simply disappear. In quantum mechanics, information can become extremely scrambled. It might become almost impossible to recover, but in principle, the information itself should still exist. So what happens when something falls into a black hole? In 1974, Stephen Hawking showed that black holes aren't completely black. Quantum effects near the event horizon can make them release a faint form of energy called radiation, now known as Hawking radiation. As the black hole releases this energy, it slowly loses mass. And eventually, according to the original idea, the black hole should disappear. But here's the problem. Hawking radiation appears to be almost completely random. It tells us things like the black hole's mass, charge, and spin, but it doesn't seem to tell us what originally fell inside. A star, a spaceship, or a library could fall into a black hole. But the radiation wouldn't seem to tell us which one it was. So if the black hole completely disappears, where does all that information go? That's the black hole information paradox. Physicist Don Page later showed why this problem becomes even more interesting. If information really is preserved, the amount of information in the radiation should first increase, and then eventually decrease as the information comes back out. This expected pattern is called the Page curve. But Hawking's original calculation suggested something different. The information would keep getting lost as the black hole disappears. So we have a strange conflict. Quantum physics says information should survive. Hawking's calculations seem to say it doesn't. And that's where the new proposal comes in. The researchers behind the 2026 study ask a simple but radical question. What if the black hole never completely disappears? Their idea is based on a version of Einstein's theory called Einstein-Cartan theory. In ordinary general relativity, space-time can bend. But in this theory, space-time can also twist. This twisting is called torsion. The researchers then describe this geometry using 7 dimensions instead of the 4 we normally experience, 3 dimensions of space and 1 of time. The extra dimensions would be hidden from us. But according to the theory, they could become important at incredibly tiny scales, especially near the Planck scale, where our current understanding of physics reaches its limits. As a black hole loses energy through Hawking radiation, it becomes smaller and denser. According to this theory, when it becomes incredibly small, the twisting of space-time could become strong enough to push back. Think of it like a tiny cosmic break. Instead of the black hole shrinking all the way to nothing, the evaporation stops. What's left is a tiny, stable black hole remnant, and it's unbelievably small. Its predicted mass is about 9 times 10 to the minus 41 kilograms. That's around 10 billion times lighter than an electron. But here's the really strange part. This tiny remnant could still hold an enormous amount of information. For a black hole as massive as the Sun, the researchers estimate that its remnant could store about 1.5 times 10 to the 77th power qubits. That's an almost unimaginable amount of information. The idea is that the information could remain stored in tiny, long-lasting vibrations of the torsion field. So instead of the black hole destroying its history, the information could survive inside the remnant. But the theory goes even further. The same 7-dimensional geometry that produces the possible black hole remnant also produces a number close to 246 gigaelectron volts. And that number is important. It's connected to the energy scale of the Higgs field, which plays a major role in explaining why elementary particles have mass. So the researchers are suggesting something remarkable. The same underlying geometry might help explain both black holes and the mass of matter. One mystery asks, what happens to information inside a black hole? Another asks, why do particles have mass? But there's an important reality check. This is not proof that black holes never disappear. It's a peer-reviewed theoretical proposal. The extra dimensions, called 7 dimensions, have not been detected, and no black hole has ever been observed evaporating. A black hole with the mass of our Sun would take roughly 2.14 times 10 to the 67th power years to evaporate through Hawking radiation. That's vastly longer than the current age of the universe. So for now, this tiny remnant exists only in the mathematics. And there are other ideas. Some physicists think the information could escape through tiny patterns hidden in Hawking radiation, without any remnant being left behind. So the deeper question is still open. When a black hole finally reaches the end of its life, does the universe erase its history? Or does it hide that history somewhere we simply haven't learned how to see yet? Or maybe a black hole doesn't end with nothing. It ends with information?